So I'd like to start my lecture on Chapter 7, Thermochemistry, with a couple of short simulations. It's from a program called Chemistry, and these spheres represent water molecules, and they've made a small droplet in a small container. Okay, so you have to imagine that this is just a droplet in a container, and then these walls are set to be at a relatively high temperature. And let's watch what happens as these molecules begin to move. So I've started the simulation. You notice every once in a while, one is able to get free from the surface. Right? And then as they hit the walls, what happens to them? They pick up energy in the form of kinetic energy. Because what's actually the wall, let me pause it for a second, what's actually in the walls are more molecules that have high energy. And so what they're doing is they transfer energy when a molecule hits them in the form of kinetic energy. Now notice the droplet here starting to get looser and looser, and I'll run the simulation some more. As they strike the wall and return over time, right, just randomly, they begin to put more energy into the droplet. And the droplet begins to move, and then eventually it breaks up, and now all we have is water vapor inside this tiny container. And the molecules are taking on sort of an average kinetic energies, like what you'd expect for gases from the ideal gas law chapter in kinetic molecular theory. So let's look at another simulation. Now, in this simulation, there's the original population of low temperature molecules. The red ones are already at high energy. So let's watch what happens when I free them from where they're at. And you can kind of imagine what will happen because these are already at high energy. Right? They split apart immediately. There's not enough attractive energy between the molecules. And what will happen is now these molecules are striking the walls and transferring energy to this liquid. And you notice how much faster that broke up. That's because there was already a lot of material in here to transfer the energy, right, to the blue molecules, which were lower in energy to start with. At some point, they're going to reach an average sort of kinetic energy, like you would expect, again, from kinetic molecular theory. So Chapter 7 intro is thermochemistry, and in thermochemistry we like to look at and study the relationship of energy to physical and chemical changes. So for example, how much energy will it take to make a certain compound, or how much energy is released when a certain compound is burned or reacts with another compound? Questions like how far can an object be moved from the energy contained within a substance is also one of the roles of thermochemistry. So many of us are familiar with chemical hand warmers. You take them out and you put them out of their plastic wrapper and you stick them in your hands, right? And they begin to heat up, and they provide sort of that relief you need on the sidelines if you've ever played sports or if you're out in the snow. Over time, they stop working, right? And if you've ever torn one open, it's full of this sort of black material on the inside. Well, let me talk first about two types of chemical reactions. We have exothermic reactions and we have endothermic reactions. And an exothermic reaction is one that releases energy. And an endothermic reaction is one that absorbs energy. So this is the reaction that we're showing down here for the reaction that takes place in a chemical hand warmer. And you can see why it's sealed up in plastic. It's just iron, right? And it's in some other material, but it's iron, pure metallic iron. And it turns out as the iron begins to react with oxygen and it obtains a little moisture from your hands, this turns out to speed up the reaction a little bit, it produces iron oxide, this is rust, and some energy. So this hand warmer reaction, actually the combustion of iron, it's actually just a slow combustion of iron. Remember, uses oxygen and produces heat. Produces some energy is a type of exothermic reaction. one of the clear signs that you have an exothermic reaction is it gets hot. So reactions that absorb energy get cold. And if you've ever used a chemical cold pack from a sports sports injury, right? And you get a sprained ankle and they take that thing out and they crack it and it starts to get really, really cold. That's actually just another kind of chemical reaction that's endothermic. Now, here's something I want you to think about, right? When we say it gets hot, what that actually implies is that the reactants started out at a higher energy than the products because that energy got released as a product of a reaction. So I had a certain amount of energy stored in this reaction, right, in terms of potential energy as it turns out, and they react to produce the product. That energy has to leave. So that's why it's exothermic. Products are lower in energy than the reactants. For an endothermic reaction, actually what's happening is the reactants are absorbing energy from their surroundings, so they produce the products, which implies the products are higher in energy than the reactants. So there's a couple of things that affect the rate at which temperature increases in these reactions, and just something to think about, right? It's the rate of the chemical reaction, and like I said, that can be sped up with moisture from your hands, and that's why it works so well if you just keep them in your hands to keep your hands warm. And the other thing is that the size of the warmer, the size of the hand warmer makes a difference because the more material you have, the more moles of reactants you have, right, the more energy that it can produce. So as with all fields, there are some very important definitions that you have to understand. And one of those is just the word energy itself. And energy is really the capacity to do work. That's actually what the word itself means. And it's something that an object can possess, like gasoline possesses a certain amount of energy in it, right? And it has the capacity to do work, which is, for example, make your car move in a forward direction or backwards direction for that matter. Okay, so it has that ability to make an object move through, for example, transformation of the energy into work. Now, so you can possess energy, but it turns out the word heat isn't something an object possesses. It's actually the exchange of energy between objects with different temperatures. So if you have a hot object, so for example, like the walls of the container that we saw in our simulation, those possessed energy, and then when the molecules struck the walls, right, they absorbed energy from the walls and picked that up in the form of kinetic energy. So that really is what we talk about when we're talking about heat being transferred between objects. It's the transfer of energy from one object to the other. And typically where we're looking at this is between two objects that have different temperatures. So if you feel an object, you can do this with lots of different things, but if you put your hand on an object and it feels cold to you, that's because you're transferring energy from your hand into the object, and typically that would be a metal object, for example, a pipe or something. Now, work is the exchange of energy by moving objects against some sort of force. Okay, so when your car is running, right, you see both heat and work energy being produced. Your car engine generates heat, which we generally give the symbol Q. And we'll talk about units and all that stuff later. But work, right, which is usually given W, is the moving of the object against the force, like drag and friction and things like that. All right, so energy can be possessed, but heat and work are forms of energy in terms of transfer of energy. Heat is the transfer between different temperatured objects. Work is the transfer essentially to make something move, okay, against a force. Now, when we talk about types of energy, we can also classify them as potential, and that would be stored energy. And you can guess that chemical energy is a stored type of energy. When we burn gasoline in the car, right, that energy is stored in the gasoline. We can also classify things as kinetic energy, and kinetic energy is the energy associated with moving objects. So you're taking gasoline in your car, right, and creating work type energy out of it, but part of that is making the car move. So gasoline is potential energy. The moving car is a form of kinetic energy. So there's a little figure in your textbook, and it makes a good summary of kinetic energy and potential energy. So to start with, at the very top, we have energy, capacity to do work. And then we can separate that into kinetic energy of motion and potential energy due to position or composition. So it's stored type of energy. Now, kinetic energy is related to movement, and if you remember looking at the video, the simulation we did, right? Thermal energy is associated with temperature differences, and transfer of energy in terms of molecular motion. Now, chemical energy, we really haven't got a good foundation of what chemical energy is yet, but it's really actually associated with the positions and attractions of electrons and nuclei of atoms. So, kinetic energy is energy of motion or energy that is being transferred, and potential energy is stored energy by virtue of position and forces of attraction or repulsion. All right, so I wanted to, I'm going to set this video up real quick. That's me in my neighborhood, and I forced my children to watch me do this because I thought it would be a lot of fun for them to see. So what I have is a basketball in my hands, and then I have a dog ball. Like, see, there's the basketball, and there's the fetch dog ball, right? And right, I'm going to be holding these together here, and there is a potential energy of the large ball, the basketball, and essentially like a tennis ball, where I'm holding it here, and I'm going to let them go at the same time. And if you've ever watched those documentaries on acceleration in Galileo and all those kinds of things, you'll know that the objects fall at the same rate. But then when they reach the bottom, one of the things that happens is the big ball bounces off the ground and then transfers all of its potential energy upwards. But the problem is there's a little ball there, and because the little ball there is there, Newton's laws basically say that when the big ball and the little ball meet, they exert equal and opposite forces to each other. So watch what happens as the little ball picks up the big ball's kinetic energy and potential energy. And I thought it was pretty funny. Anyways, yeah, that's kind of the idea, right? I had an object that had. All right, so I wanted to. I'm gonna set this video up real quick. That's me in my neighborhood, and I forced my children to watch me do this because I thought it would be a lot of fun for them to see. So what I have is a basketball in my hands, and then I have a dog ball. Like, see, there's the basketball, and there's the fetch dog ball, right? And right, I'm going to be holding these together here, and there is a potential energy of the large ball, the basketball, and essentially like a tennis ball, where I'm holding it here, and I'm going to let them go at the same time. And if you've ever watched those documentaries on acceleration in Galileo and all those kinds of things, you'll know that the objects fall at the same rate. But then when they reach the bottom, one of the things that happens is the big ball bounces off the ground and then transfers all of its potential energy upwards. But the problem is there's a little ball there, and because the little ball there is there, Newton's laws basically say that when the big ball and the little ball meet, they exert equal and opposite forces to each other. So watch what happens as the little ball picks up the big ball's kinetic energy and potential energy. And I thought it was pretty funny. Anyways, uh, yeah, that's kind of the idea, right? I had an object that had a potential energy when they were held above the ground, and that was the attraction to the earth and their mass, right? And then they fell and they hit the ground. So what was happening as the ball is falling, right? It's gaining. I had heard something weird. Sorry. It's gaining kinetic energy, and as it gains kinetic energy, it's losing potential energy. Okay, so when that big ball hits the ground, it has the little ball riding on top of it like this, right? And so as it springs off the ground and begins to move upwards again, this little ball meets it on the way down. There's an equal and opposite force where they meet, and the little ball goes flying up in the air. Now, this demonstration is actually a demonstration of the law of conservation of energy. So, in essence, I had potential energy of a big ball and a little ball. And then as they fell, both of them translated their energy into kinetic energy. And when they bounced up, the little ball actually took all the kinetic energy of the large ball and itself and transferred it up into the air. Now, again, when it goes up in the air, right, that is a form of potential energy, and I suppose we could have measured the height and calculated the energy and maybe shown a law of conservation of energy there, but I think I'll leave that up to your physics professor. So, just to finish off this slide, right, in any process, chemical or physical, in any process, both chemical or physical, the energy present at the beginning must be present at the end. And the only difference is how the energy is distributed, right? So the little ball had all the energy as kinetic energy on its way up, whereas when they were coming down, they both had a certain amount of potential energy. They struck the ground. The big ball essentially stopped moving, and all the kinetic energy was in the little ball. So you could make statements of conservation of energy, right? All the potential energy at the beginning was equal to the kinetic energy of the small ball. The way they're showing it here in TRO is you could have a spring, right? And you can use mechanical energy, potential energy, and store it into the spring. So you're using your chemical energy in your body, actually, and you're storing the energy in the spring. And when you let go of it, the spring extends, and the ball goes flying, and this is now all kinetic energy. So what you could say in terms of conservation of energy is the energy of the potential energy of the spring is equal to the kinetic energy of the ball.